Okay, thanks for the introduction, Marcus. So indeed, my name is Eric Hanus. I'm project manager working at CEA, and my talk today will be about R&D that we are performing at CEA on pressurized water SMRs. So my talk will be divided into four parts. A brief introduction about SMRs, and then I'll be focusing on the new watch project we're developing in France, and which is aiming at providing electricity. One slide about a European ELSMO project that is devoted to licensing issues that are important, as we already mentioned, for SMRs. And finally, I'll be ending up my speech with the R&D that we are developing at CEA on SMR hybrid system dedicated to heat or hydrogen applications. So just one slide about the SMR and the challenges and success factors that we are facing. Clearly, what you see on the figures, it's a traditional scale effect, which explain why, for instance, in France, we've been increasing the unit power from 900 to 1300 and now 1650 megawatt with the EPR. And that has a positive impact on the leverage cost of electricity. So obviously, if we want to be competitive with SMR, and that's our target, we need to operate on three levels. The first one is to act on the conception, to have a simple and safe conception. I'll be showing that for the new word. We are aiming at integrated architectures, and that will help us reducing the initiating events. And also one advantage with SMR is the small size with the low residual heat that can be released through passive safety systems. Sometimes we often forget that the M of SMR means modularity. And clearly modularity has to be taken into account at the early stage of conception and also in the manufacturing process. By that, you'll be having modules that are manufactured and tested in factories. Then they will be transported into containers. And this procedure will allow a reduced on-site construction time. And finally, the third level is about standardization and series effect. So clearly, if you promote a product, you want to have the same product, whatever the operator or whatever the country. And to achieve that, you need some standardization, normalization, and also in the licensing procedures. And if you end up with that, you will benefit from a serial production effects on components and on your program. Now, let me explain you the product we are developing now in France, which is called the New World project. So New World is a 300 electric megawatt power plant, including 2 reactors. It is an integrated reactor. As I mentioned earlier, we benefit from an integrated architecture where you have the steam generators, the pressurizer inside the pressure vessels. This pressure vessels is integrated in a metallic containment, which is immersed in a water basin, as you can see on the right-hand side. To give you some ideas, the pressure vessel is the same size of a 900 electric megawatt. And the containment, it's typically a sphere of, let's say, 15 to 16 meter diameter. With that program, with that project, what market are we aiming at? Clearly, we want to provide low energy, low carbon energy, flexible power generation, complementary to renewable intermittent sources, and large nuclear power plants. We're not opposing the two. The market we want to replace is the coal-fired power plants that are in the range of 300 to 400 electric megawatt. We'd like also to power remote municipalities and large industrial sites. And also a supply network that can be fitted with larger size reactors. So that slide is quite important, and I'll take some time to describe it properly with you. It's about the technologies and innovations that we are developing within the New World project. So clearly our ambition is to have this innovation within the product. Once again, I mentioned integrated architecture. What's the positive impact of these architectures? Clearly, you have the primary cooling system inside the RPV, which means that clearly you reduce the risk of loss of coolant accident. To give you an idea, the pipe connected to the vessel, the maximum one is 30 millimeter, so which is clearly very, very small. Another challenge we have developed steam generators with a plate design. And that's clearly a differentiating issue because it allows us to have the most compact design worldwide. Another item is the immerge control mechanism. All the control bars are within the vessel. By doing that, since you have the same pressure all around, you eliminate the rod ejection risk. I already mentioned that with SMR, you have a small residual heat to remove, and you can do it passively. And we do that with the system we call RRP, with a heat exchanger inside the vessel that is connected to the condenser, which is cooled down with the water wall I mentioned around the containment. About the core, we're developing a soluble boron-free core, and that obviously avoid any clear water plug because we have the same chemistry everywhere. And also it induces simplification in the effluent treatment. The containment, which is metallic, has also a high level of tightness, and it's immersed in a water wall, which is nice for the protections. Finally, the nuclear island building, it's semi-buried, which is also an advantage when considering external hazards. Now, I won't go into detail, but just to give you an idea about the roadmap and the partnership around New World. We've been performing some feasibility for studies for, let's say, 10 years now. We have finalized a pre-conceptual design phase in 2019. And at the moment, we are in the middle of the conceptual design phase. Our roadmap ends up with a New World product that will be available to meet market needs by 2030. The project is led by EDF, Électricité de France, with its strategic partners, so CEA, Naval Group, Technicatom, and it's got the support of the French government. We have some funding at the moment from the French Economic Recovery Plan. And this project is open to international cooperation. The name of the project, New World, which means nuclear forward, has been launched at the IAEA General Conference in September 2019. And at the same conference, we signed a framework agreement between EDF, CEA, and Westinghouse to explore potential cooperation on SMR development. Now, one word about licensing. We already mentioned that issue with former speakers. It is an important one. What we did with several partners within Europe is that we've proposed, and the proposal was accepted for a fund by the European Commission with the Euratom program to develop this ELSMO project, which aims at creating methods and tools for European stakeholders to assess and verify the safety of light water SMRs that would be deployed in Europe. I don't think I will go down in the work package breakdown structure. I don't have time here, but since I'm attending a Nordic conference, and thanks for that, I just want to mention that we have Finn's partner here with Fortum being in charge of the WP6 devoted to the synthesis and recommendation of the whole project. And we also have VTT that is acting as a project manager. Now, I move on to the last part of my talk, dedicated to new applications, that is to say hydrogen and heat. So within the energy transition program, where many countries aim at reaching carbon neutrality by 2050, like in France, we have launched at the CEA a new research field on PW SMR and hybrid systems. This research area can be split into 4 axes, and we have placed under axis 1 the market studies, and that to us is clearly important. We're not pushing for technology push, but we are willing to answer a market demand. So this axis will help us to identify the needs either on hydrogen and heat. And we are trying to forecast ourselves in the 2040, 2050. It will help us to define the expected performances for these innovative systems. Axis number 2 and axis number 3 are pretty similar, one dedicated to hydrogen projection and the other one to heat application. So in both axes, we'll be defining systems where SMR can be coupled to high temperature electrolysis, or we could work also on preconception studies of heat supply SMR concepts. In both cases, we'll be evaluating the performances of these new systems, evaluate their cost, and then compare them to the market analysis from axis 1 to check that we will be answering the needs, and obviously we'll be performing some system safety studies. Finally, we have identified an additional working program on energy conversion systems. Clearly, we need to have in mind that this kind of SMRs will be integrated in an energy field with other sources like PV, wind turbines, fuel cells, and the energy conversion systems will be providing power, heat, hydrogen, drinking water. So this system has to be studied, and it can also be optimized when considering a different kind of storage like batteries, thermal energies, or gas. So now, let me give you some trends that we have already found regarding hydrogen. So hydrogen, if we aim to have a decarbonated hydrogen production, we have 2 targets: the mobility vector, so transport, and also decarbonate the current industrial hydrogen production. So the idea here was to set up SMR. So let's say a 450 thermal megawatt, and couple it to a HTE, so solid oxide electrolysis cell hydrogen production. If we do that, we end up with a figure of around 100 tons a day. That corresponds to a fleet of 20,000 cars, or let's say 1,200 trucks. 100 tons a day, it's about 35,000 tons a year. And for the French market today, it's only 4% of the national production. So it's quite limited. And if you make some forecast in 2035, it's only 1% of the French production. So what's important also to stress here is that at CEA, we are working on both bricks, both technological bricks. First, the HTE, which provides high yield and requires both electricity and heat. And we can also use this technology in some cases to power, in the reverse way, to provide power. And we're developing the second brick, SMR, and it can work in a cogeneration mode, providing heat and electricity. And the size of the unit, it's consistent with a hydrogen production unit and could answer local needs. If we go into more details on this slide, you can see the integration we can have between the two systems, the SMR and the HTE SOEC. So the same scenario as the one I mentioned before, providing 100 tons of hydrogen a day. What we see here is that the electrolyzer needs some power and also some heat. The ratio is the following. It's about 7% of thermal energy compared to the 93 remaining heat that is converted with the turbine into electricity. So at the moment, we have the two schemes. On the left-hand side, the SMR, and on the right-hand side, the HTE. And we have identified different ways to couple both systems with different intake points to take heat from the Rankine system of the SMR. And we can also work on different supply mode, which can either be direct or indirect supply mode. And also when coupling more intimately the two systems, we can benefit from the waste heat from the HTE and bring back some heat to the SMR. Now, if I move on to the heat application, so at the moment, the idea we have is that district heating is quite diverse in Europe. I just want to share with you this figure where you can see on the y-axis the share of renewable energy and recovery in the district heating. Against on the x-axis, the share of district heating in the global heat consumption. So typically you have, like in France and Spain, you have countries where the share of district heating is rather small versus the global heat consumption. In the opposite, you have, like Germany or Poland, a higher share of district heating, but these are mainly fossil-fueled district heating. And that's nice for you Nordic countries. You have these dots on the right-hand side of Northern Europe, where you have well-developed district heating, and they're rather green. If we look now at some more deeper evaluation in two countries, France and Finland, to give you some figures about the global demand. In France, we have identified it's about 450 terawatt-hours for district heating, and the size, typical size, is about 40 thermal megawatt. In Finland, there was a presentation from a colleague of yours, Professor Yverinen, 2 years ago, who tried to figure out how SMR, nuclear SMR, could fit in within this district heating segmentation in Finland, and he proposed two types of coverage with pretty large unit at 120 thermal megawatt and a lot of smaller units around 24 thermal megawatt. How does that end up with technical studies? What we did first at CEA, we've set up some functional requirement for the small modular reactors for the district heating type with a nominal power, indeed quite large, 100 thermal megawatt, providing liquid water at 110 degrees and getting water back from the district heating grid at 70 degrees. The design we are working out now has no primary pump. It has no boron within the core management, and it allows load following from 30 to 100% demand. And it relies on passive safety designs. The come up of the studies written here on the figures. What's very interesting is clearly the temperature are pretty low. you end up at the primary circuit with an inlet temperature at 100 degrees and outlet temperatures at 160 degrees, and which is very nice is associated pressure, only 10 bars. So that gives us very interesting perspective with such low temperature and pressure when we want to dimension all the components and the economics behind that. And currently, to take into account the market aspect I've just shown you previously, we are moving our studies to downsize the nominal power from 100 to 20 thermal megawatt. What are the perspectives? So clearly, the objective of this R&D work is to bring some techno-economics data to evaluate the feasibility of such SMR hybrid system to propose a carbon-free solution in a moving multi-vector use of energy. So we don't know at this stage what we will be ending up with. SMR working cogeneration, working to deliver power when the electricity prices are high, moving to heat deliveries, having a hydrogen production, storage, but that's the system we want to work in. And I just mentioned here a small note that within the next Euratom call, which is where you have some drafts circulating at the moment, we are promoting at CEA a proposal to work on this issue of SMRs with heat and hydrogen applications. Finally, I'll be concluding my talk to summarize that the R&D activities at CEA on PW SMRs are participating in the industrial New Watt project, developing R&D on a hybrid SMR system to decarbonize heat application and hydrogen production, and promoting project at European scale, elsewhere, and hopefully a next proposal for the coming call. Thanks a lot for your attention.